Good morning. How's it going? Welcome back. Today we have quiet classroom. So let me know if there's anything online that you want to see, or if you're joining with questions or problems or anything. Mostly us. Last project is in project 5 or project number 4. Like last as in previously turned in, or last as in next to turn in. We could take a look right now if you want. Here, let me take a seat since it's just a few of us here. There we go. All right, so let's come down to project number 5. All these guitar string vibrations. Morning.
Scared her off?
I think so, yeah. Let's see, what do I have here? All right. So I've got some setup for like doing beam bending analysis. And this is the same kind of setup as the reading in the first. I think the second reading kind of looks at this. Yeah, static deflection of an elastic beam. So we're modeling like the neck of the guitar as a beam, and it's cantilever. So it's fixed on one side, and then there's some kind of force applied on the other one. So coming down here, we have something like this, like a fixed support, but then instead of a distributed load, we have a moment applied right here, all the way at the end. So I know how big the moment is, and that's going to give me all my boundary conditions there. So let's do this. We're going to say, oh, that one's a solution, at least one. I want to take this equation my computer's moving slow today. Spectacle. So for static beam, we have E, I, W, 1, 2, 3, 4 equals 0. So all the accelerations of W are all 0. So that's static beam deflection like that. And then let's take a look at our boundary conditions. Coming back up here. Let's just copy this guy. Oh my god, there we go. Copy image. Paste this in here. So I know if I take this beam and split it up, let's just start off with 1, 2, 3. So 1, 2, 3, 4, 5, 6. I want to do 6. So 1, 2, 3, 4, 5, 6. So each one of these positions, this is like W0, W1, W2, W3, W4, W5, and W6. It helps to kind of split it up like this, like make it a small problem first, and then we can always look for the like any kind of symmetry or repeating structures that happen there. So I don't need to solve for W0 because this is equal to 0. And I don't need to solve for W, well, all right, so W prime is also 0, and that's going to be helpful when I try to figure out what's happening at W1. But first, we'll just, and then there's no shear, no shear at L, so W triple prime of L is also 0, and then W double prime at L equals M over EI. So we're going to need definitions for first, second, third derivatives. So W prime is WI plus 1 minus WI minus 1 all over 2 delta X, or we'll say 2H, since we're just using that H. W double prime is going to be WI plus 1 minus 2 WI plus WI minus 1 all over H squared. And here, let's write this in so we know. And then W1, 2, 3 of I is going to be equal to, let's go back and check. I need that third central derivative here. That one I usually forget. First and second I got, but third derivative, I feel like I So third derivative central, so minus 2 and a plus 2. and then 2h cubed. And what was it? I plus 2, I plus 1. Was it minus then plus? Yeah. All right, so the reason that I'm writing out all these derivatives and then I have this fourth derivative up here is this is going to help us figure out what are the equations that we need to solve for this finite difference method. So at I equals 1, that's the first w that I'm trying to solve for. I have w of 3 minus 4w2 plus 6w1 minus 4w0. That one I know is already 0, plus w of negative 1. W negative 1 I don't know, but I do know that at w0, this is 0, and that has to be equal to w of 1 minus w of negative 1. So w1 equals w negative 1. So I can erase that negative 1 and put in a 1, which makes this thing, instead of saying 6w1, now I have a 7w1. So I can start erasing some stuff because I don't have a w0 and I don't have a 6, now I have a 7. And all that is equal to 0. So my first equation is that one. Now I have w4 minus 4w3 plus 6w2 minus 4w1 plus w0. And again, that one is 0, so I can erase it again. And all that is equal to 0. I equals 3. I've got w5 minus 4w4 plus 6w3 minus 4w2 plus w1, all equal to 0. So this is one of the first ones where boundary conditions are not affecting the equation. w6 minus 4w5 plus 6w4 minus 4w3 plus w2 is all equal to 0. This is the last equation where boundary conditions are not affecting it. So 3 and 4 are right in the middle, and they only, all those fourth derivatives only depend on everything that's in the beam. So the boundary condition is not directly affecting those equations. So then I equals 5. We have w7. And w7 is a made up, I'm going to put it as like a circle here. It's a made up value that is going to depend on boundary conditions at w6. So that one we're going to have to figure out what is w7 based on boundary conditions at w6. We'll come back to that in a second. Minus 4w6 plus 6w5 minus 4w4 plus w3. It's all equal to 0. So let's figure out how we find out that w7 term. So I know that w triple prime equals 0. So W6, 1, 2, 3 equals 0, which is equal to W8 minus 2W7 plus 2W5 plus W4, and it's all equal to 0, so that's just what it's equal to. But now I have two unknowns, W8 and W7, so I don't want to plug in. Oh, did we get the wrong sign? It should be W1 equals W-1. I think we're right for there. You mean in that first I equals 1 equation? Oh, W triple prime. Oh, there's a wrong sign. Is it supposed to be positive 2, negative 2? Do a quick Google search, double check. Let's see. Higher order, oh my god. No, I just want a list. So third derivative. Oh, minus 1 plus 2. Oh, I see. So it should be a minus minus, a minus plus minus, minus plus, and then minus. I think like that. So a minus, a plus, and a minus 2. Minus plus minus, like that. Plus minus minus. Yeah, as long as it flips back and forth, I think we're good. So then we also know W double prime of 6 equals our applied moment over EI, which is going to be W7 minus 2W6 plus W5 all over H squared. So MH squared over EI plus 2W6 minus W5 equals W7. So now I can plug that in to I equals 5. So that second derivative is going to tell us what that W7 is. I can replace it with positive 2W6. So now this 6 becomes an 8. and then a negative W5. Oh wait, my bad, I erased the wrong thing. So negative W5 becomes a 5W5 and a positive 2W6. Now the 4 becomes a 6. And then all of this is not equal to 0 anymore. It's equal to a negative h squared m over ei, like that. Finally, our last equation is at I equals 6. So now we've got W8 minus 6, minus 4W7 plus 6W6 minus 4W5 plus W4 is all equal to 0. But we don't want that W7 in there. We're going to get that one out of the way. So that's going to be the same, so negative 4. Oh man, let's put that over here. So 4 times mh squared over ei plus 2w6 minus w5. Let's get rid of that. So a 4 here. Now this is 8 and this is 4. Minus 4. So we've got minus 4w5 on both sides. So I'll get rid of this one. And then an 8w6 on this side, so that becomes a negative 2. And then I have that w8, which is now going to be (2w7 minus 2w5 plus w4). I know it seems like it's a lot of work, but once you get the pattern, you only have to do this once, and then we can make it as big or as small as we need to be. This is one of the benefits. Like, finite difference works just as well as finite element, but with finite element, all of this like boundary condition kind of stuff is taken care of in your shape functions, so you don't have to worry about all of these like boundary condition setups. But once you do it a couple of times, it's all about the same. All right, so let's get that W8 plugged in there. So 2W7 minus 2W5 and a plus W4. So now this is a 2W4. And that 2W7, I got to plug in again. So negative 2, so now this becomes a negative 4. Get rid of that W5. And then 2 times 2, so this 4W6 minus 2W6 becomes a positive 2W6. And then this 2mh squared, now this becomes 2 times that mh squared. Phew! All right, now we're making some progress, believe it or not, because I've got all these finite difference equations, and I can set it up. I'm going to zoom out some, and let's do this. Take all that, move it over here, make it smaller. Because I want to take all of this and turn it into an equation. So here's my W1, W2, W3, W4, W5, W6 equations. And then equation 1, 2, 3, 4, 5, 6. So in my first one, I've got a 7W1, a negative 4W2, and a 1W3, and then a 0, 0, 0. And then in my next equation, I have a negative 4W1, 6W2, a negative 4W3, and then a 1W4, and then 0, 0 there. Now equation 3, I've got 1, negative 4, 6, negative 4, 1, and 0. And this is where we're starting to see the pattern develop, where there's going to be negative 4s along this diagonal and negative 4s along that diagonal, except for when we have those boundary conditions, it might get a little wacky. Then the next equation, that I equals 4. Now I've got a 0W1, 1W2, negative 4, and then a 6, a negative 4, and a 1. I equals 5. I've got a 0 and a 0, and then a 1, a negative 4, 6, 6W5. Oh wait, 5W5, and a negative 6. W6, and this is where our boundary conditions are starting to change those terms, and then a 0, a 0, a 1W3. Is that one right? Oh no, it's not right. I need a 0, 0, 0, and then a 2W4, a negative 4W5, and a 2W6. And all that is going to be mostly zeros, except for down here, I've got that negative m over e I h squared, and then a negative, or a positive too. I think it's positive. And the first row and the last two rows are always going to be the same, and the rest of the rows are all going to be, like, no matter if I have 60 rows or I have 6 rows, first row will always be like this. This is always going to be row number 1, and then these are always going to be the last 2 rows, or at least, like, well, we have to fill up as many zeros as we need, but that's, the pattern is still going to be there, unless we made a mistake and I'm doing it on the fly, so it's possible. And what did we say? So we do have n. I want to stick with 6 for now. So I can double check. And then dx is going to be L over n plus 1, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, no. L over n. And along the diagonal, I want 6's. 6 times I just want to make a vector called 1s that is that size. Let's do multiple rows. And I'm gonna use that diag command to shift it by plus or minus, and then np dot diag of 1's bracket 2, 2. Let's just take a look at the A that we have so far. We have an error that happens. It doesn't like spaces after the Let's make this bigger. So I have the general form that we need: 6's along the diagonals, then -4's, and then 1's along those different diagonal terms. But I want to replace that first row and the last row with the terms that I need. So bring that back over here, and I'm going to say, really just the first row, all I need to do is say that A00 is 7, and that'll take care of that first one. We can double check. Sure enough, there's a 7, -4, then a 1. So that's my first boundary condition that I set up. Well, I mean, I set up 2 boundary conditions on that side, but. And then the next thing that I need to do is say a bracket -1, -1 equals 2, a bracket -1, comma, -2 equals 2. Let's see if that does what I wanted it to. So it should be 2. Nope, I messed that one up. -3, column -3. I want to go back 2 spots. Like that. Alright. And then the last thing is that a bracket -1, -2 equals +4? No, -4. Oh, so that one was fine. Oh, we want row -2 and column -1. That one's supposed to be positive 6 or negative 6. So now it's at least matching what we wanted it to. Oh, and we also need a negative 2 to be 5. All right, now we're pretty sure we're in business. Oh, thanks, Koa. And then my right-hand side is going to be zeros, the size of n, but right-hand side, negative 2, is m times, what do we call it here? dx squared over e over I, and right-hand side, negative 1, m is 2 times m times dx squared over, oh yeah, this one's negative, and I think this one's positive. A comma RHS. Let's see what we find. Oh, it would help if we had run this first command. It looks a little off. Did I mess up a sign? I definitely messed up a sign somewhere in there. I think it was this last one. Nope. Nope, did not like that. I mean, we're solving for something. I don't know what we're solving for, though. Something wacky is going on. Because it should just be like a parabola. It should basically look like a parabola. But I messed something up along that finite difference process. So it's definitely somewhere in those last two equations, because the first boundary condition on the left-hand side looks like 0 slope and 0, and w is 0 and the slope is 0. So that one, the first two equations should be right, but these last two definitely made an error somewhere along the way. So W7. That's W3. And now W7, I'm going to plug in so let's get rid of that, equals negative mh squared over e I negative 2w6 positive w5 So 6 becomes 5. -2, add -2 to -4. That should be a -2. So this one should have that shouldn't be -6, this should be -2. Let's see if that fixes. Much better, yeah. So now whether we're using 6 or 60, it's the same setup for the code to work on that, to get it through there. Because we set up the same kind of symmetric matrix and then just replace the first 2 equations and the last 2 equations. And depending on how big the derivatives are for the boundary conditions, sometimes you only need the first equation, sometimes you only need the first 2 equations or last 2 equations. But if I change this back to 60, or sorry, 6, then it's still the same solution. Only difference is now just, yep, going in there. Yep. And if we're trying to demonstrate convergence, we've done that a lot in this class, but one way we can do that is merge these 2 together, merge, and now take this whole, everything below here, tab it over, let's see, do I have x in there? No, I have dx. Just give it an x value. So now instead of 1, I'm going to say and let's do this. Put some squares in there. Huh, looks like it's all the same. Is it just converging too quickly? Look, I think it looks pretty good no matter how small our steps are. Let's do 6 and 60. I mean, we're using a finite difference to approximate the solution that is a parabola, so it's pretty exact even on our first try. Is that what's going on? I think so. Yeah, even that first solution for like 3 data points, it's all converging to the same answer. So it works pretty well. Anything else? Sorry, we were running through like this first problem on the project. Is there anything else that we're working on or had questions on? Yeah. Just catching up on an email. Yeah, that's fine. Yeah. Yeah. Closing. The only difference is with the W, when you just tell it to plot it, it's just going to plot versus the dx. So if you create, I just made like dx times a range. Now it's how it comes to it. A probably is 1 to n. It may help to plot this in reverse order. Yeah, so we can see 3 on top of 30 on top of 60, and they're all like at a given position, it's all the same answer. It's nice when things work out that way. And all right, yeah, I don't want to start a whole nother project. But on Friday, if we want, we could run through the last part of the project, or work on anything else. It's our week. This is the time to work on whatever we want. Thanks for joining.